Welcome back, everyone. I have another example I'd like us to work through together. In this example, we're asked to solve the rational inequality when is the quantity 3x plus 3 over the quantity 2x plus 4 greater than or equal to 0. And so this is going to be very, very similar to the process we used for solving our polynomial inequalities that we discussed in an earlier section. And it's actually basically the same conversation, right? We could think of this as our rational function f of x is equal to 3x plus 3 over 2x plus 4. Go through the whole process of graphing our rational function and then just figuring out when is our graph on or above the x-axis. That is definitely one way we could solve this rational inequality, but we can cut out a lot of that work. We don't actually need the whole graph. We can break it down into just a sign chart instead. And so it's basically going to be a lot of the same steps that we have over here in our graphing procedure. We're just not going to put it all together and sketch the graph. We're just going to create a sign chart with that information instead. So let's go ahead and get started with that. Our first step is still the same, finding our x-intercepts, because the x-intercepts are a place where our function can switch signs from positive or negative. And so our x-intercepts occur only when the numerator is equal to 0. So when is 3x plus 3 equal to 0? Well, when x is equal to negative 1. All right, so next up are our vertical asymptotes. That's when our denominator is equal to 0. So we have to solve 2x plus 4 equals 0. And well, that's going to have a solution when x is equal to negative 2. The next step in our graphing procedure is to figure out the end behavior of our rational function. But the end behavior of our rational function isn't going to cause our function to switch from positive to negative or from negative to positive. So when it comes to solving a rational inequality, we can actually leave that part of the procedure out, right? We don't really care if the end is going up towards positive infinity or negative infinity or some slant asymptote or anything like that. All we care about is it positive or is it negative? So that information is not actually necessary for these inequality problems. And so now our third step is going to be altered a little bit as well. We still need to pick some test points between and beyond our x-intercepts and vertical asymptotes to actually figure out the signs of everything. But then we're not going to use that information to graph. We're going to use that information instead to create a sign chart. So on the bottom of our sign chart will be our important x values, the ones corresponding to our x-intercepts and vertical asymptotes. And above, or on the top of our sign chart, we'll actually put the sign, positive, negative, or other information about our function. So we're looking at really the sign of 3x plus 3 over 2x plus 4. So the important x values that we know of are x equals negative 1 and x equals negative 2. So at x equals negative 1, we have our x-intercepts. That's when y is equal to 0. So we'll include that x value as part of our solution set. At x equals 2, though, at x equals negative 2, though, we do not have a 0. We have a vertical asymptote. So I'll denote that on our sign chart with VA. The important reason to denote that on a sign chart here is our function is not defined at x equals negative 2. Right, that's where our vertical asymptote occurs. So negative 2 has no chance of making it into our solution set. However, x equals negative 1 is going to be included because our inequality accepts when the whole function is equal to 0. All right, so now we're ready to pick some test points, and unfortunately my green pen is dying on me, so let me go ahead and switch that to pink. So for our test values, we just need to pick a x value between and beyond our vertical asymptotes and x-intercepts, or within each of these subintervals. So we need something to the left of negative 2. I went ahead and chose negative 3. We'll need something between negative 2 and negative 1, like negative 1.5. And then our final one, we'll need a test point to the right of x equals negative 1. And this is where I'll use x equals 0, or my y-intercept, as a nice test point. All right, so if I take a moment to plug these three different x values into our rational function up here, the outputs that we should find are when x is equal to negative 3, we get an output of positive 3. So that means every x value to the left of our vertical asymptote is going to create a positive output. If we plug in x equals negative 1.5, testing our middle region here, we get the output of negative 1.5, meaning all of these x values are going to produce a negative output for our rational function. That's not what we want here, so those won't make it into our solution set. And then for our final subinterval to the right of x equals negative 1, we used our test point of 0. got the output of positive 3/4, but more importantly, we got a positive output. So now we need to actually write down the solution to our inequality, which we can basically read off from our sign chart. So our solution, if we're using interval notation, could be written as so. We're allowed to include these positive solutions because that's greater than 0. So that'll go from negative infinity all the way to negative 2. But we cannot include negative 2 because of that vertical asymptote. Our function is not defined there. We have more to our solution set though. From negative 2 to negative 1, our function is always negative. That is not greater than or equal to 0, so it cannot be allowed in our solution set. But once we are at negative 1, we've obtained that value of 0. We are equal to 0, and that is allowed in our solution set. And then anything to the right of x equals negative 1, anything bigger than x equals negative 1, will also work. So that goes all the way to positive infinity. So here is the solution to this rational inequality using interval notation. The open interval from negative infinity to negative 2 in union with the half closed interval from negative 1, including that left endpoint, to positive infinity, not including that endpoint. We never include the endpoints when infinity is involved. So that's basically how we can adapt our graphing procedure for rational functions to help us instead solve rational inequalities. Basically the same steps. You could actually cut out the end behavior step altogether because it's not necessary for finding where signs switch. And then you create a sign chart instead of a graph. Or if you wanted to, you could graph the whole thing, go through that whole procedure, and still find the solutions to your inequality.